Welcome to AlgoRush. You know, every single data system out there, from the contact list on your phone to a massive search engine, is built on one thing, a fundamental blueprint for how it stores information. Today, we're going to break down that blueprint and look at the critical storage decisions that dictate a system's speed, its reliability, and ultimately, its success.
All right, so here's our roadmap for today. We're going to kick things off with the core storage dilemma. Then we'll dive into where data actually lives. Is it memory or is it disk? After that, we'll see how it's organized, clear up a common mix-up, and then we'll wrap it all up with why these layout decisions are just so incredibly important.
Okay, so right at the very beginning, every single data system, doesn't matter if it's a simple app or a massive cloud service, has to answer one core question.
And you might think, well, how hard can that be? But it turns out this simple question has massive consequences. Choosing a storage strategy isn't just some minor detail. It has long-term and honestly often irreversible impacts on performance, on consistency, and on how complex the whole system is going to be to operate down the line.
So let's get into our first major decision, the physical place where the data is actually going to reside. Is it going to live in super fast but kind of forgetful memory, or on a slower but much more permanent disk? And this right here really lays out the fundamental trade-off, doesn't it? On one hand, you've got memory, or RAM. It is ridiculously fast, but it's volatile. If the power goes out, poof, your data is just gone. On the other hand, disk is way slower, but it's persistent and a whole lot cheaper. This is the classic battle between speed and durability. This quote just nails it. This is the core challenge for any in-memory system. How do you get that lightning-fast performance of RAM without living in constant fear of losing everything every time there's a crash or a power outage? Well, the solution is a really clever technique called a write-ahead log, or WAL. The best way to think of it is like a system's diary. Before it makes any change to the data in memory, it first writes down what it's about to do in this log, which lives on the durable disk. It's how you get the best of both worlds. And this process is the key to making everything safe. First, you log the change you want to make to the durable disk. Then you apply it in fast memory, and only after that log entry is safely written can the operation be confirmed as a success. So if a crash happens, the in-memory data might vanish, but that log acts as a perfect recovery script to rebuild everything. Okay, so we've decided where to put the data. Now let's explore the next critical choice. How do we organize it? This is where things get really interesting for performance. When you and I think about data, this is usually what we see, right? A simple, clean table. You've got your rows, you've got your columns. We see a user and all their information is laid out right there next to them. But under the hood, what the computer is actually storing can look very different. So in what's called a row-oriented system, all the information for a single user, like Leslie here, is stored together in one continuous block. The system stores the ID, the name, the email, and the last login for user 101 all in a row. This layout is absolutely perfect when you need to grab an entire record at once. Think about loading a user's complete profile page. You need all the data for that one user, and the system can just grab it in a single, super efficient read.
But a column-oriented system completely flips this concept on its head. It organizes the data in a totally different way, grouping all the values from a single column together.
So here, all the user IDs are stored together in one block, all the names are stored together in another, and so on. Now this layout is incredibly efficient for analytical queries. Just imagine you need to calculate the average last login date across millions of users. The system only needs to read that one block of login data, completely ignoring all the names and emails. It makes the query blazing fast.
So the key point here is this: there is no single best layout. It's all about using the right tool for the job. Row-oriented layouts are built for transactional workloads, what we call OLTP. Column-oriented layouts are built for analytical workloads, or OLAP. The choice you make depends entirely on the kinds of queries your application is going to be running most often.
Now speaking of layouts, let's take a second and clear up a common point of confusion that trips a lot of people up, especially when it comes to the terminology. This is a really important distinction to make. I know the names sound almost identical, but wide column stores and columnar stores have very little in common under the hood. It is a classic case of confusing terminology. So this visual shows how a wide column store actually works. A great way to think of it is as a big nested map. You have a main key, which in this case is a URL. Within that key, you have groups of data called column families.
But here's the crucial part. All the data for that single URL is stored together. So even though it has column right there in the name, its layout is fundamentally row-oriented. So, what's the big picture here? We've looked at where data lives, and we've looked at how it's organized. Why are these architectural blueprints so incredibly important? Here's the most important thing to remember. These fundamental storage choices, memory versus disk, row versus column, are not just small implementation details. They dictate a system's core strengths and its weaknesses. They determine whether your application flies or just grinds to a halt. Getting this choice right at the very beginning is one of the most important decisions you can possibly make.
And all of this leaves us with a fascinating question for the future. We have built entire systems for decades around this trade-off between fast, volatile memory and slow, persistent disk. But what happens when that trade-off starts to disappear? Are the foundational rules of data storage